So now let's look at the half-life for a first-order reaction. The half-life is defined as the time required for a reactant to decrease to half of its initial concentration. If you started with 1 molar concentration, how long does it take to get to 0.5 molar? Half that. Well, when we look at our integrated rate equation, this guy up here, what if we solve this equation for T? Just solve it for T. And when we do that, we find we get T equals 1/2 natural log of concentration of A naught divided by concentration of A. But since we're dealing with half-lives, the concentration of A is 1/2 the concentration of A naught. The definition of a half-life, the initial concentration is dropped to 1/2 of its original value, which means T equals 1 over K times the natural log of concentration of A naught divided by the concentration of A naught over 2. Or T equals 1 over K times the natural log of 2. Natural log of 2, plug in the calculator. T 1/2, we've changed this T to a 1/2 because we're talking about half-life. T 1/2 equals 0.693 divided by K, the rate constant. Okay. Note, when we've done this, this is independent of the initial concentration. It doesn't matter what your initial concentration was. If you have a reaction and you calculate the half-life to be, say, 2 minutes, to go from the concentration of A naught starting at 2 molar to 1 molar would take 2 minutes. To go from 0.5 molar to 0.25 molar would also take 2 minutes. It's half of the original concentration. The time it takes to get to that is the half-life. All right, well, let's do some math. So let's look at the decomposition of ethane, C2H6, into methyl radicals. This is a first-order reaction with a rate constant of 5.36 times 10 to the negative fourth seconds to the minus 1 at 700 degrees Celsius. Question, what is the half-life of this reaction in minutes? Well, half-life equation is very simple. First order, there's only one variable, the rate constant. So T 1/2 is 0.693 divided by that rate constant. Plug in the rate constant in the equation. Note you will get this answer because our rate constant is in 1 over seconds. Our answer, 1.29 times 10 to the third seconds, has to be converted into minutes. 1 minute per 60 seconds gives you 21.5 minutes. That was a pretty easy problem. Right now you're saying, hey, can't we make this problem a little bit more difficult? Well, I'm happy to oblige you there. But before we do that, note, what's up with that 700 degrees Celsius? Where's the temperature in here? Well, in this problem, temperature doesn't matter. The temperature is just in there to give us the reaction conditions, but it's not part of the math we're going to do. And I know you're saying, but wait, I want to do math with temperatures in it. Don't worry, before this chapter is out, we will be doing mathematical equations that have temperatures, and you will be happy. All right, well, but let's spice this up a little bit. Let's look at the reaction of A goes to B, which has a half-life of 20.0 seconds. Question, how long until the reaction is 87.5% complete? Note, if it's 87.5% complete, that means 87.5% of our starting material has been converted into product. But with these equations, we don't want how much product there is, we want to know how much reactant is still in there. How much reactant has not been converted to product yet. So what that means is if it is 87.5% complete, that means there is 12.5% of A, our reactant, still in there. Okay. So, how do we solve this problem? Well, let's go through the straight grinding it out before we look at a slightly easier way for this particular example. Let's grind it out. Well, what do we know? We have two equations. We know the integrated rate equation, natural log of A naught over A equals KT for first order. We know the first order half-life equation, T 1/2 equals 0.693 over K. What are we after? We're after how long it's going to take to get 87.5% complete. Well, that's not half. That's not 50% complete. So it's looking like we're going to need this equation over here, and we need to solve for t. Well, we know the reaction is 87.5% complete. 12.5% of A is still in there. Therefore, we can reduce this part of it to the natural log of 1 over 0.125. Natural log of 100%, or how much starting material we had, divided by 12.5%, how much is left. But if we do that, we don't have this K yet. We're after T, we don't have K. However, using our half-life equation, we know that if it's a 20-second reaction, just put 20 seconds in for our half-life, because our half-life is 20 seconds, and then that will allow us to calculate K as 0.03465, plug that K into there, and now we can complete our math. Natural log of 1 over 0.125 equals 0.0347 times 10 times T, the time. The time is 60.0 seconds. All right. Now with this problem, it turns out there was a slightly easier way to do it because of the way half-lives work. Note, if we start with 100% of A, after 20 seconds, one half-life, we would be down to 50% of A left. Well, what would happen in another 20 seconds? Well, 20 seconds is another half-life, which means if we are at 50% A, 20 seconds later, we will have half of that. 25% of A is left. The reaction is 75% complete. Well, what happens if we wait another 20 seconds? Well, then we would have half of this. But what's half of 25%? 12.5%. It turns out for our problem, we are landing on a half-life, a 12.5%. That is the third half-life. So 20 seconds to get to 50% left, 20 seconds to get to 25% left, 20 seconds to get to 12.5% left, means 60 seconds to get from the beginning to 12.5% left. 60 seconds is our answer, which is our answer here that we got with all the math. So it might be a good idea for first order to remember where all of the percentages that lie on half-lives. So it's 50%, 25%, 12.5%, 6.25%, and if you're feeling crazy, you might go all the way to 3.125%. All right, that made this problem a little bit easier. Note, though, it would have been easier because we landed right on a half-life. How long did it take to 87.5%? Makes this problem a little easier. How long to get to 6.25%? That's a fourth half-life. That would be 80 seconds. But what if I said how long to get to 90%? Do any of these half-lives start at 90% of A remaining, or 90% complete, meaning 10% remaining? No, it dropped from 12.5 to 6. So if this was something like 90% complete, you would have to do it this top way. You would have to use the math because it's not falling right on a half-life, which would make it easier. Okay. Well, that's it for a first order reaction. Let's look now at second order reactions and go through all of it again in terms of the integrated rate equations and half-lives. Good news, we're not going to do the math. We're not going to do the derivations. Let's just look right into it. Okay, for a second order reaction, we can look at it this way. Consider A goes to products. Well, the rate of the reaction is negative change in concentration of A with the change in time. The rate law, if it's second order, means there's a 2 there. And yes, we are going to set these two equal to each other and do some integration. Note that you could have had an A plus B goes to products, and if the rate law was rate equals K times concentration A times concentration of B, that would also be second order. But the math to get to the second order rate equation is just too complex. It's doable for all you math junkies. I'm not a math junkie, so I'm not going to do it. I'm just going to cut to the chase. And here's the chase right here. For a second order reaction, the integrated rate equation is 1 over the concentration of A equals 1 over the concentration of A naught plus KT. There's our math, our integrated rate equation. The half-life equation for a second order reaction is T1 half equals 1 over K times the concentration of A naught. Here we have a very important point in the difference between first order and second order half-lives. Second order half-life does depend on our initial concentration. The more concentrated your solution is, the faster it's going to get to the first half-life. The second half-life is actually going to be longer than the first half-life because the concentrations are different. Okay. Graphically speaking, though, recall with a first order half-life, if you graph the natural log of the concentration of A versus time, you got a straight line. With a second order reaction, if you graph the natural log of the concentration of A versus time, you do not get a straight line. However, if you graph 1 over the concentration of A versus time, you will get a straight line. This second order integrated rate equation, y equals mx plus b, right here, there's our equation for a straight line, but you have to graph 1 over the concentration of A. And so here's a nice way, if you're in the lab and you're not sure if you've got a first order or a second order reaction, first graph the concentration of A versus time, then graph the natural log of the concentration of A versus time, then graph 1 over the concentration of A versus time, and whichever one gives you a second line tells you what order your overall reaction order is. If 1 over A versus time gives you a straight line, it's second order. All right, so let's work on some examples. Here's a question. 2 iodine atoms in the gas phase will react to form I2 in the gas phase. This follows second order kinetics and has a rate constant of 7.0 times 10 to the 9th molar minus 1 second minus 1 at 23 degrees Celsius. That's right, no temperature to worry about now. That's just giving us reaction conditions. Question, 2 of them. If the initial concentration of iodine was 0.086 molar, calculate the concentration after 2 minutes. Second question, calculate the half-life of the reaction if the initial concentration of iodine is 0.6 molar, and then calculate it again. Oh, it's actually 3 questions. Calculate the half-life again if the initial concentration was 0.42 molar instead. All right, first question. If we start with 0.86 molar, calculate the concentration after 2 minutes. Well, it's second order. We're told it's second order, so we need this as our integrated rate equation. We're after the concentration after 2 minutes, so that's this A, this 1 over A, is this concentration is A, equals 1 over 0.086 molar, our initial concentration, plus K, we were given K, and T, 2 minutes times 60 seconds per minute. And while this math isn't too hard, but realize when you take this and multiply this and then add that to 1 over this, you have not calculated the concentration of A. You have calculated 1 over the concentration of A. Make sure you then calculate the concentration of A. The long way is to multiply A by both sides and then divide this side by the results of this calculation. Make sure you're actually calculating the concentration of A. If you leave your answer as 1 over the concentration of A, that's wrong. The question is, what is that concentration of A? And at this point is 1.2 times 10 to the minus 12th molar. All right. Wow, 1.2 times 10 to the minus 12th. It started, what did it start with? 0.086 molar, and now we're at 1.2 times 10 to the minus 12th molar. Because if we look at this rate constants, it's 7 times 10 to the 9th per molar per second. That's a fairly large number. This is a very quick reaction. All right, the second part of this problem then is calculating the half-lives. Well, let's look at if the initial concentration of iodine was 0.6 molar. Well, T1/2 is 1 over K times concentration. Put in your rate constant, put in your concentration, and you get the half-life is 2.4 times 10 to the minus 10th of a second. Note if we're down to 0.4 molar, we do the same thing, putting in 0.4 here, and we're at 3.4 times 10 to the minus 10th of a second. Note, lower concentration, slower half-life. And really, that's all there is to the second order problems. Truthfully, the math for the second order problems is just a little bit more complicated than the first order problems due to this whole 1 over the concentration of A, but it's not undoable math. You have the abilities to do this math. The last thing to throw in here, your book kind of throws it in there, so I might as well too. We can have zero order reactions where the reaction does not depend on the concentration of any of the reactants at all. The reaction just goes, and it doesn't matter what the concentration of any reactants are. For those types of zero-order reactions, and I personally don't know of any of them, but I'm sure they exist, the rate equals K. There's no concentrations in there. And if you get the integrated rate equations, it is just the concentration of A equals negative KT times concentration of A naught. So this is a case where if you actually did graph the concentration of A versus time, you get the straight line. That would be the case for a zero-order reaction. All right, we will continue in the next video with activation energy.